Hey everyone, this is the host with Minute Earth, and this is the story of every engine like all engines ever in about 60 seconds, really quickly. The earliest ancestors of engines were basically tubes made out of clay that ancient humans started using around 8,000 BCE to suck up water from the ground. These early humans had figured out that when there is a hole at the bottom of a container and a hole at the top of a container, water will flow from the bottom to the top all by itself. It doesn't take any work. And not long after that, they realized that if you attach a second container to the bottom of the first one, the water will just keep flowing indefinitely. Boom, perpetual motion. Well, not quite. You need to get that second container below the first one for gravity to do its work. But still, that's pretty darn clever. And these suction devices eventually evolved into the Archimedes screw, invented around 250 BCE by the Greek mathematician and inventor Archimedes. This was a big step up because it could move water uphill. The screw was basically a tube bent into a spiral shape, and rotating it would pump water up to whatever height you needed. Still, it wasn't until around 1000 CE that someone came up with the idea of putting a windmill on top of an Archimedes screw to make a fully automated water pump. And that technology spread along trade routes throughout Europe and Asia. In China, Persian and Indian engineers combined the Archimedes screw with water wheels to build elaborate irrigation systems. And in Europe, windmills were used to pump water out of mines and eventually to grind wheat and other grains. By the Industrial Revolution, windmills were already several centuries old. But the windmill's role as a grain grinder was soon taken over by the water frame, which was powered by, well, wait for it, water power. Okay, so we talked about how people figured out how to use gravity to move water up using the principles of suction and the Archimedes screw. But harnessing the energy of moving water to do work was a different kind of leap. But once water was turned into a mover of things, everything changed. Some of the earliest water wheels were overshot wheels, where a bucket or scoop attached to the wheel would catch the water falling from a height and then drop straight down, turning the wheel as it went. Other early water wheels were undershot, where the falling water hit the bottom of a wheel that was partially submerged in the water. That wheel would rotate until the water hit the top of the wheel and spilled off. Overshot wheels are more efficient, but undershot wheels can handle really, really fast-moving water. And both types were used extensively in mills to turn grain into flour. A single water wheel could power multiple millstones at once. And at their largest, water wheels were over 40 feet tall and 20 feet wide, spinning at nearly 15 revolutions per minute. Water power was also put to work in factories starting in the late 1700s. Water frames powered looms that created textiles much faster than they could be by hand. And steam engines, which we'll get to in a minute, were also sometimes directly connected to water wheels to increase their efficiency. Even today, water wheels remain a common source of renewable energy, especially for small-scale electricity generation. But meanwhile, something else was happening in the world of engines. In 1678, the British scientist and physicist Robert Hooke published a paper describing a device he called an engine area reciprocating engine. Basically a piston that moves back and forth inside a cylinder, pushing against a spring, which then turns a crank, which rotates back and forth. It's simple, elegant, and it works, kind of. Hooke's engine was never built during his lifetime, but the concept stuck around. Fast forward a few decades and boom, the steam engine. In 1712, the English engineer Thomas Savery patented the first crude steam engine. It could pump water out of mines, but it was bulky and dangerous and inefficient. Then, in 1769, the Scottish engineer James Watt improved upon it and basically invented the steam engine as we know it. Watt's steam engine consisted of a boiler with a piston inside, which would heat water into high-pressure steam. That steam would push the piston out, which would then turn a crank that was connected to a flywheel. The steam would then pass through a valve into another chamber, where the pressure would drop, allowing the piston to slide back into place, and then the whole thing would start over again. It was an ingenious solution to the problem of how to turn linear motion into rotational motion, and it was a huge hit. Watt's steam engines pumped water out of mines and drained swamps and powered factories and, most famously, trains and ships. Steam power was so revolutionary that it truly was the engine that built the modern world. But there was still a lot of waste in the process. For every pound of coal burned, only about 1% of the energy was actually turned into useful work. The rest was lost into the air as exhaust heat and noise. Enter the internal combustion engine, also known as the Otto cycle engine, named after the German inventor Nikolaus August Otto, who received a patent for it in 1876. Instead of heating water into steam to do the work, the internal combustion engine burns fuel, mixes it with air, and then detonates the mixture, forcing the piston out. That's why we call them combustion engines. The pistons of most internal combustion engines are connected to cranks, which rotate the crankshaft, which ultimately powers the wheels of your car or the propeller of a plane. And it's way more efficient than the steam engine, converting between 17 and 25% of fuel into motion. For a while, steam power remained popular for large stationary applications like powering generators in plants, which makes up for the inefficiency by burning massive amounts of fuel. But for smaller portable applications, internal combustion engines became the norm. They powered cars in the late 1800s and motorcycles in the early 1900s and airplanes in the mid-1900s. Today, the vast majority of the world's vehicles run on internal combustion engines. Then, in the late 1950s, engineers looking for even more efficiency developed the Wankel engine. It is also known as a rotary engine because instead of pistons moving up and down inside a cylinder, the Wankel engine has a triangular-shaped rotor that spins inside a housing. Fuel is sprayed onto the rotor, which explodes and pushes the rotor around in a circle. Early Wankels were promising, powerful and smooth, but they leaked a lot of power out the sides as heat and noise. So they never caught on for automobiles. But nowadays you can find Wankel engines in some specialized applications like helicopters and fighter jets and submarines and even audio equipment. In the meantime, engineers have also been trying to harness the power of controlled explosions in a different way. In 1909, the Swiss engineer Alfred Toka developed what we now call the diesel engine, which uses compression ignition rather than spark ignition to burn fuel. No spark plug means less parts and less weight. And instead of the gasoline, diesel engines run on diesel fuel, which is cheaper and more energy dense. Because the fuel ignites on its own, diesel engines are simpler and heavier and slower to start than gasoline engines. But they're more efficient at turning fuel into motion, especially when it comes to heavier vehicles. Diesel power now dominates the trucking industry. Some cars and motorcycles run on diesel too. And diesel engines are still used for generating electricity, powering ships, and even running locomotives. Then there's the electric motor, which has been around since the 1800s and uses electricity to spin magnets and move a shaft. The electric motor is efficient, clean, and quiet, and it has no emissions, which is good news for the planet. What it lacks in cool factor, it makes up for in practicality. Electric motors are everywhere, in vacuum cleaners, hair dryers, washing machines, fans, toys, robot vacuums, and even bikes. More and more cars are being powered by electric motors too, which means that the next time you're stuck in traffic, you might be surrounded by future history. Every engine is different and each one has trade-offs, but together they've powered our world from the simplest tools to the most complex machines. And knowing how they work lets us decide which ones to use and lets us invent new ones, which is great news for humanity and for stories that can be told in under 60 seconds. Speaking of which, thank you for watching this Minute Earth. This video was made in partnership with a digital studio. They've produced hundreds of fun science interactives for major museums including the Smithsonian. And now they're partnering with us to bring those interactives to you for free online. Head to the website to check out their interactive exhibits on everything from space photography to special effects to plate tectonics. And thanks for watching.